Hello viewer, welcome to this massive open online course on engineering mechanics. Today I will discuss on kinetics of particles. So what are the learning objectives? So after completion, participants will be able to know the approaches in understanding the concept of kinetics. State Newton's second law of motion and D'Alembert principle, and we will be able to discuss the application of equation of motion in rectangular coordinate, normal and tangential coordinates and cylindrical coordinates. Now, first of all, let us see what is kinetics. Kinetics is a section of dynamics which deals with the relationship between the change in motion of a particle and the forces that causes this change. Now, in earlier module, in module 9, I have discussed about the kinematics of particles, where I have discussed regarding the displacement, acceleration, but I have not discussed about the causes of that motion. Okay. Now, kinetics is the cause. So, kinetics deals with the forces which is responsible for the change in motion of a particle and the forces that causes this change. Now, there are four approaches in understanding the concept of kinetics. They are Newton's second law of motion, D'Alembert's principle, work and energy, and impulse and momentum, linear and angular, both related to this impulse and momentum, linear, angular principles. Okay. In this unit, I will discuss regarding Newton's second law of motion and D'Alembert principle and its application. Now, let us see the famous Newton's second law of motion. It states that when an unbalanced force acts on a particle, the particle will possess accelerated motion in the direction of the force with a magnitude and is proportional to the force. Okay. Now, this acceleration of a particle is proportional to resultant force acting on it and is in the direction of this force. So, if we use symbols, so F is proportional to A. So, F by A we can write is equal to m. M is nothing but mass or constant of proportionality, and it is always a positive scalar. Now, most important point to be considered in Newton's second law of motion, m is constant. So, during any acceleration provides the concept of inertia. So, quantitative measure of the resistance of the particle to a change in its velocity. So, Newton's second law can be written as F is equal to ma, and it is nothing but the equation of motion. Now, when more than one force acts on a particle, the resultant force is considered as vector summation of all forces, that is Fr, that is the resultant force, is equal to summation of F. So, in general case, the equation of motion can be written as summation of F is equal to ma. So, now example of equation 2 to have some concept. Let us consider a particle is acted upon by two forces F1 and F2, and it is due to this it is having a acceleration a. Now, this, if we draw the free body diagram and kinetic diagram, it is represented in this figure 1b, and resultant of these forces actually produces the vector ma. So, it can be represented by this kinetic diagram. Okay. So, ultimately resultant of this force produces mass and acceleration. So, another important part, if this resultant of this forces is equal to summation of force is equal to 0, then the acceleration is also 0. So that the particle will either remain at rest or moving along a straight line path with constant velocity. So, this condition is the famous condition we know, the condition of static equilibrium, and it actually gives us the concept of Newton's first law of motion. Now, again D'Alembert's principle, it is very important, especially we know summation of F is equal to ma. So, it is a dynamic equation. Okay. But if summation of F minus ma is equal to 0, that dynamic equation is converted into static one and very useful for solving numericals related to equation of motion. So, this vector minus ma is known as inertia force vector, and this state of equilibrium is known as dynamic equilibrium. Now, another important concept, inertial reference frame. So, what is that? It is important to note that acceleration of a particle is to be measured with respect to a reference frame either fixed or translates with a constant velocity when equation of motion is applied. So, the concept. Now, here in this figure 2, a observer with a velocity v0 and the particle with having a acceleration a. Now, for example, an observer will not accelerate, and measurements of acceleration of the particle will by the same from any reference of this type. So, this figure 2 shows that concept. So, this type of frame of reference is known as Newtonian or inertial reference frame. Now, examples. Real life example, that is study of motion of rockets and satellites, and this inertial reference frame is considered to be fixed to the star and satellite. Another example, dynamic problems concerned with motion on or near the surface of the earth using an inertial frame which is assumed fixed to the earth. So, this concept is very much needed. Okay. So, now here equation of motion for a system of particle. The equation of motion here, let us consider several masses. Okay. So, it can be extended to a system of particles isolated within an enclosed region in space. Okay. Now, here it is actually experiencing two forces, one is force Fi and small fi. Okay. So, consider the ith orbitary particle with a mass mi is subjected to a system of internal forces and a resultant external force. So, inertial force is the minus small fi is the resultant of all forces that the other particles exert on the ith particle, okay, especially. So, here in this case the resultant external force is capital Fi is nothing but the effect of gravitational, electrical, magnetic or contact forces between the ith particle and the adjacent bodies or particles not included within the system. So, here in this case, let us the free body diagram and the kinetic diagrams for the ith particle are shown in figure 3b. Here actually applying the equation motion, we can say summation of F is equal to ma, and also now let us consider summation of F means what? The external forces capital Fi plus summation of Fi all these forces experienced by the ith particle is equal to nothing but mi ai. So, when the equation of motion is applied to each of the other particles of the system, similar equation will result, and if all these equations are added together vectorially, we obtain summation of Fi plus summation of small fi is equal to summation of mi ai. Now, it is to be noted that the summation of the internal forces, that is summation of small fi, will equal to 0, as internal forces between any two particles occur in equal but opposite collinear pairs. So, ultimately only the sum of external forces will remain, okay, and the equation of motion can be reduced to summation of capital Fi is equal to summation of mi ai. Okay. So, now again let us consider the center of mass. Okay. Now, in this figure here, if Rg is a position vector which locates the center of mass g of the particle. So, it is evident from this figure 3a. Then by definition of the center of mass, we can write mRg is equal to summation of mi Ri, where m is equal to summation of mi is the total mass of all particles. So, now let us differentiate the above relationship twice with respect to time, with the assumption that no mass is entering or leaving the system. We get MAG is equal to summation of mi ai. So, putting in equation 4, we obtain summation of F is equal to MAG. So, this equation, from this equation 5, it is evident that the sum of external forces acting on the system of particles is equal to the total mass of the particles times the acceleration of its center of mass g. So, equation 5 actually provides justification of application of the equation of motion to a body that is represented as single particle, and this is a very important logic. Okay. Now, let us consider rectangular coordinate. So, suppose a particle moves relative to an inertial xyz frame of reference, and the forces acting on the particle along with its acceleration may be expressed according to their ijk components when equation of motion is applied. So, ultimately if we apply the equation of motion, so we can have summation of F is equal to ma. This is the main basic equation. So, from that let us consider the inertial this xyz frame. So, we can write summation of Fxi plus summation of Fyj plus summation of Fzk is equal to m into Axi plus Ayj plus Azk. So, let us consider again, let us have these scalar equations. So, scalar equations are like that in x, y, z, summation of Fx is equal to max, summation of Fy may, summation of Fz maz. So, this gives only the magnitude. Okay. So, again let us consider again this equation of motion applied to normal and tangential coordinate. Suppose a particle moves along a known curve path, the equation of motion for the particle may be expressed in the tangential, normal and binormal direction. It is evident from this figure 5. Okay. So, but it is to be noted that as the particle is constrained to move along the known curve path, there is no motion of the particle in binormal direction. Okay. So, this is the condition, that is the equation of motion can be applied in curvilinear path considering normal and tangential coordinates. So, here again in this case the equation of motion, again let us take the equation of motion summation of F is equal to mass into acceleration. So, based on that we can put all the forces in tangential. So, in the tangential direction we can take summation of Ft with the unit vector ut plus summation of Fb ub plus summation of Fn is into un, it is the unit vector ut ub un is equal to mass into acceleration in the tangential direction and plus mass into the acceleration in the normal direction. So, but the equation is satisfied provided this condition, summation of f t is equal to m a t, summation of f n is equal to m a n, and summation of f b, that is the binormal, the summation of force is equal to 0. So, equation 7 shows the equation is satisfied by this condition. Okay. So, now again in this case another important point let us consider, at is what? It is nothing but dv by dt. It represents the time rate change in the magnitude of velocity. It is already I have discussed in module 9. Okay, what is this curvilinear motions and others. Okay. So, this acceleration term we have got it from that, but if summation of f t acts in the direction of motion, the speed of the particle will increase. Further, if it acts in the opposite direction, the particle will eventually slow down. Okay. So, this is another important realization for that. So, another concept, the acceleration in the normal direction, it is now we know v square by rho. Rho is the center of curvature, the radius of curvature. So, represents the time rate change in the velocity's direction. Now, it is important, it is happened when summation of f n always act in the positive n direction towards the path center of curvature, and this force is known as centripetal force, okay, and directed towards the center. Now, again let us come back to the cylindrical coordinates. So, in the cylindrical coordinate we can find when all the forces acting on a particle are resolved into cylindrical component, that is along the unit vector u r, u theta and u z, the equation of motion says, again applied to the summation of f is equal to m a, we can write this equation, summation of 4 in the radial direction, force into radial direction into the unit vector along this r, then summation of force theta f theta u theta plus summation of f z u z is equal to mass in radial direction, acceleration in the radial direction with this all unit vector. This is the relationship. Okay. Now, but to satisfy this equation we need summation of f r is equal to m a r, summation of f theta is equal to m a theta, and summation of f z is equal to m a z. Okay. So, now let us discuss some example related to application of equation of motion. Now, suppose a 50 kg crate shown in figure A rests on a horizontal surface for which the coefficient of kinetic friction is mu k is equal to 0.3. Now, if the crate is subjected to a 400 Newton towing force as shown in figure, determine the velocity of the crate in 3 seconds starting from rest. Very good problem, application of this equation of motion can easily be done. Let us see the this figure A. Okay. So, this towing force P is equal to 400 Newton and it is making angle theta with the 30 degree with the horizontal. So, this is now the free body diagram if we draw. So, by applying the second law of motion. Okay. Now, let us apply first the concept of kinematics. Okay. Now, to solve numericals related to kinetics, we must have the knowledge of kinematics. So, that is why before starting this module 10, you have to study the module 9. Okay. Now, in this equation, free body diagram we have drawn, weight of the crate, this, then frictional force F, mu NC, NC is the resultant reactions, and acts to the left as it opposes the motion of the crate. Always we know frictional force acting in the opposite to the motion of the crate. And okay, and here two unknowns is equal to A and NC. Okay. So, always when we will solve the problem related to equation of motion, we have to always find out what are the unknowns, and then after finding out the unknowns, we have to find out the known units, so that we can find out the unknowns. So, one of the most important thing in solving numericals related to dynamics, statics, whatever may be, the drawing of the free body diagram. Okay. So, now in this equation of motion, forces along x direction max, we have resolved it. Okay. Now, in fy direction we have resolved it. Now, equation 2 and substituting the result in equation 1 and solving for yield, we will get NC value, the unknown, 290.5 Newton, and acceleration 5.185 meter per second square. So, this is one of the solution, okay, to find out the acceleration. Now, again let us consider kinematics. Okay, we have to find out that acceleration is constant and applied force P is constant. So, initial velocity is 0. So, the velocity of the crate in these 3 seconds, we can apply the kinematics relationship V is equal to V0 plus ACT. So, from that putting the value, ultimately we are getting the velocity 15.6 meter per second. So, this is the answer. So, this is how we can solve the numericals related to equation of motion and to find out the unknowns. Now, let us take another example. Here in this case, determine the a racing car, determine the banking angle theta for the race track, so that the wheels of the racing car will not have to depend upon friction to prevent the car from sliding up or down the track. Assume the car has negligible size, a mass m, and travel around the curve of radius of rho and with a constant speed v. Okay. So, now first of all free body diagram let us draw, see the figure D. Okay. Now, considering the free body diagram, okay, here NC represents resultant of the ground on all 4 wheels. So, equation of motion using NB axis, we can write normal directions. Okay, we can we got the relationship in angular by NC sin theta is equal to m v square by rho, and in the binormal directions we got the relationship NC cos theta minus mg is equal to 0. Now, from this relationship equation of motion, we can easily find out the angle theta by eliminating NC from and m from these 2 equations. By dividing equation 1 by equation 2, we get this theta is equal to tan inverse v square by Gp. So, this is another very important relationship for the application of equation of motion. Now, here another important problem here. Here we have considered a frictionless step pulley mounted at the top of an incline, supports a block A restrained to slide over the incline and a block B hanging from it. Okay. Now, what is the problem? Problem is that if the block of mass 3 kg should accelerate at 2 meter per second square up the incline, determine the mass of the block part A if the incline is frictionless, and part B if the coefficient of dynamic friction between the incline and block A is 0.3. Now, let us see. Let us find out the let us draw the free body diagram. In the figure F, it is clearly drawn. We have shown the tension in the string for both the cases, step pulley. Okay. Tension at A, tension at B, and the free body diagram, all aspects. So, assuming the step pulley to be frictionless as well as massless, the tension in the cords are such that the summation of their movements about the center of rotation vanishes. This is the condition. So, we can write twice Ta minus 4 Tb is equal to 0. So, Ta is equal to twice Tb. This is the most important relationship. Now, from the free body diagram, we can find out for frictionless incline, resolving it in in this case summation of force is equal to ma. So, we have resolved Ta minus ma g sin 30 degree is equal to ma aa, and for block B mbg minus tb is equal to mb ab. Okay. So, from kinematics also we can consider, we have got the relationship acceleration b is equal to twice aa. So, from that we got the acceleration of b. So, putting this in equation 1 and 4, in equation 2 and 3, we can get the relationship and we can get the expression for Tb. Tb is tension at B is nothing but 10.36 Newton, and from 6 we got the mass of this block B is 1.78 kg. Now, for frictional incline, same relationship, only we have included 0.3 Ra in the equation number 7. So, from that actually again solving it, we have got the expression, the value for this magnitude of Ta is 28.36 Newton. Now, again applying the for frictional incline, applying this equation of motion, ultimately we have got from equation 8 and putting from equation 1 Ta is equal to twice Tb, we can get this relationship and we got this expression or the magnitude of mb is 2.44 kg. Now, one of the most important thing, summary of the result, because when frictionless incline Tb is equal to 10.36 Newton, mb is 1.78 kg and Ta is equal to twice b 20.72 Newton. But for frictional incline Ta is increased. Okay. So, Ta is here 28.36 Newton, mb is 2.44 kg and Tb is equal to 14.18 Newton. So, it may be noted that the presence of friction force on the incline results in considerably higher tension in the cords and requires a larger mass on the hanging block to cause same acceleration on the block in the incline. That is why here important, in the first case frictionless incline, the mass of B is 1.78 kg, but for frictional incline this mb is 2.44 kg. So, dear participant, dear viewer, most important thing today I have discussed about the incline, this equation of motion applications and this Newton's second law of motion application. This is very important for the case of kinetics, and these two books, Engineering Mechanics by K.L. Kumar and Engineering Mechanics by R.C. Hibblard, is very important book you can follow for your conception. Thank you very much.